Hello everyone, we are studying the topic of transistor amplifiers, and in this chapter we are going to see how we can build voltage amplifiers using BJT and MOS transistors. In general, the simplest signal processing task is amplification. Amplifiers are used with transducers or sensors because usually the output signal of transducers are weak. As a result, they are not suitable for a reliable signal processing. To help with this problem, amplifiers are used to amplify the output signal of these transducers and increase the magnitude of the signal. In this course, we're going to learn about how we can force the BJT or MOSFET transistors to operate in the region that is suitable for the purpose of using them as a voltage amplifier. This process is called biasing. So we're going to learn how we can bias these transistors to use them as an amplifier. Here are two example amplifier circuits implemented using a MOSFET and a BJT. In the below graphs, I provided the simulation results of the response of these two amplifiers to a sinusoidal input signal with the peak-to-peak amplitude of 200 millivolts. As you can see in the graphs, in both of these amplifiers, when an AC signal with a small amplitude of 100 millivolts is applied to the transistor amplifier, the output is also going to be a sinusoidal signal, but the amplitude of the output is going to be increased compared to the input signal. In both of these two amplifiers, the gain is about 3. So the amplitude of the output signal divided by the amplitude of the input signal is about 3 volts per volt. So it's slightly less than 3 volts, but it's about 3 volts. So these two are just one configuration of transistor amplifiers. In the MOSFET amplifier, the input signal is applied to the gate using this capacitor, and in the BJT, the input signal is applied to the base using this capacitor. The output in the MOSFET amplifier is taken from the drain using this capacitor, and the output of the amplifier in the BJT is taken from the collector through this capacitor. Because in these two configurations, the input signal is applied to the transistor using a capacitor, this configuration is called AC coupling. We're going to learn about how we can apply these signals to the transistor amplifiers in the future lectures. We are also going to learn about the structure of these amplifiers and how to design them. The important thing to note in this lecture is that the output signal has the same shape as the input signal, with the difference that the magnitude of the output is greater than the magnitude of the input signal, and in addition, there's a pi phase shift on the output signal compared to the input signal. So the output is the inverted and amplified version of the input signal. Next, let's take a look at the transfer function of the desired amplifier circuit. For an amplifier circuit who has the gain of 3 volt per volt, the transfer function is going to look like this one. So V out over Vi is going to be equal to 3 volt per volt. What we want to do is to look at the transfer function of our transistors and look for a region in which the output and input have a relationship like this graph. The graph on the right is the transfer function of the amplifier circuit that we studied in the past. Here is VDD, and it is connected to a drain resistor, and this is Vi applied to the gate. This is my source, and the output is taken from the drain. So this transfer function represents the input-output relationship of the top circuit. The graph on the left shows my desired transfer function, a transfer function for a linear voltage amplifier. So I'm trying to see if there is a region in the transfer function of this MOSFET transistor that looks like the transfer function of a linear amplifier. MOSFET transfer function is nonlinear in general, but it looks like in this region, these two transfer functions look similar. That means if we can make sure that MOSFET operates in the saturation region for all the values of the input signal, then the input and output are going to have a linear relationship with each other. Let's take a look at a simple MOSFET amplifier circuit and see how we can use the transfer function to relate the input voltage to the output voltage. Here is this simple MOSFET amplifier circuit. There is a AC signal VGS applied to the gate of this transistor, which is in series with a DC voltage source that we are going to represent with uppercase V, uppercase GS. These are applied to the gate of transistor and the output is taken from the drain of this MOSFET. We would like to find the response of this MOSFET circuit to an input voltage that can be represented as a constant value plus the signal value. We're going to show the constant value with uppercase V, uppercase G, uppercase S, and we're going to show the signal value with small v and lowercase g and lowercase s. And we will represent the total voltage with small v and uppercase G and uppercase S. So the input voltage consists of a constant part and the signal part, and we are going to make sure that the transistor operates in the saturation at all times, meaning that for all values of VGS the transistor is going to operate in the saturation region. Here we have an example waveform for VGS. It consists of a DC value or a constant value, uppercase V, uppercase GS, and an AC signal that is superimposed on this DC value. We are going to show that with small VGS. And the total waveform, we are going to show that with small v and uppercase GS. Let's take a look at the response of this circuit to the given input voltage waveform. We would like to use the transfer function to find the response of this circuit to the example input signal. This is what we had before, this input waveform, and this is our transfer function. We would like to use the transfer function to find the output. In the transfer function, the x-axis represents VGS and the y-axis represents VDS. The amplitude of VGS changes in this range. If I want to represent it on the transfer function, I can select these 2 points depending on my value of DC value, the constant value VGS, and I can show that the amplitude of total VGS changes in this range. So it gets slightly less than DC value and it gets slightly greater than the DC or constant value. So if I extend the maximum possible VGS value here and extend the minimum possible VGS value and find the counterpart of them for the VDS using the transfer function, I can get something like this. So for this small change in VGS, I expect to get a larger change in the value of VDS or the output signal. And if you compare these two together, you can see that the small changes in VGS is going to result in the large change in the VDS value. The output waveform or VDS is also made of a constant part DC value, this VDS, and a signal response that we are going to represent with small v, small ds. So VDS has a constant part and a time varying part. Constant part of the response is only related to the constant part of the input voltage. This is called the Q point of the transfer function, and this Q point is when the time varying part of the input waveform is equal to 0 and the time varying part of the output waveform is equal to 0. In other words, this small VGS is 0, small VDS is 0. That point is called the Q point of the transistor. And the other thing to note is that the shape of the time varying portion of the response or small VDS is similar to the VGS. In summary, we saw some examples of using MOSFET or BJT devices as linear voltage amplifiers. We saw some simulation results of using these devices to amplify AC signals with small amplitude applied to these devices and getting a similar AC signal but amplified and inverted at the output of the device. Thank you for watching.